Okay, hello, AP Calculus class. This is obviously Mr. Bosquet, and this is the first of many recorded lectures that you'll get over the next few weeks. This particular lecture is on rectilinear motion. That is motion in a line, rectilinear motion, and how you might be expected to be addressed with questions in May about rectilinear motion. You should have a handout in front of you, which will be this particular one. It shows two free response questions, one from 2000, one from 2005. Now they do say BC, but these exact same questions were on the AB exam. Often in years they will have questions on the same question on both the AB and the BC tests. So we're going to be looking at these. And I've got them here on my smartboard. One is dealing with two runners, the 2000 problem, moving along, and the other one is dealing with a car traveling on a straight road. The key in both of these is that a straight road, rectilinear motion in a line, or runners running on a straight racetrack. Now, as an aside, for the BC folks, yes, you do have to know rectilinear motion, just like the ABs do, but for AB, we're motion on the line only, so we might have a particle moving along a line. In the BC curriculum, you're also responsible for motion in the plane. So conceivably, not this lecture and maybe not the next lecture, but you might be responsible for trying to analyze motion as it moves around a plane. Certainly not at the AB level, and we're not going to mess with that today, but for the BC folks, you'll see that a little bit later. Okay, let me pause this for a second. Okay, I think we're going again. Okay, rectilinear motion, motion in the plane. Now, when you're dealing with problems like this, you might want to think of the position of a particle as a function of time being given. For example, I might have 10 minus 1/2 x squared. And this would represent the position of a particle, say on a y-axis. And it's not too terribly hard to sort of graph this thing. Let me just mention at this point, you should have your calculator available. So go to your calculator and enter in this equation, 10 minus 1/2, I can use 0.5 if I want, x squared. So this is, hopefully you realize from Algebra 2 that this is a parabola. And it's an upside down parabola because of the negative quadratic term, upside down. And you might even just imagine, ooh, this is silly, Joe. I've got 10 minus 1/2 x squared. I want this to be a function of t. So let me go ahead and pause this for a second. Okay, sorry about that. 10 minus 1/2 t squared. Certainly we want this to be a function of t. So if we look at it on our calculator, again, we have the calculator, we have it entered in. Now notice that in graphing or in function mode, we have to use y's and x. Here's the picture in the standard window. And we have a parabola. If t is equal to 0, the y coordinate is 10. Let's suppose for this particular motion problem, I only want to consider the t values bigger than or equal to 0. So that would translate over here, go to window, and I want the smallest x to be 0. And so we see, here's the picture now. And the particle now is got various y values. You can sort of imagine if I said what was y of 0, you would plug 0 in here. And so 10 minus 1/2 0 squared, which is 10. That would correspond to the vertex of the parabola. If I said, what is y of 1? Again, you 10 minus 1/2 of 1 squared, which is 9.5. And again, you can sort of follow along on here pretty easily if you hit the trace button, and then put x is equal to 1, and that gives us y is 9.5. Now again, remember on the calculator, it's thinking y's and x's, but we're thinking y and t. Y is a function of t. Now, one of the things that's most confusing for students is when they look at the graph, it looks like a parabola. The particle is not moving in a curve. The particle is moving on the y-axis only. And there's sort of a trick to sort of analyze this. If you go to your calculator and hit the mode button, and what I want to do now is go down to parametric mode, the PAR, select that, parametric mode, and then go back to y equals. Now we actually get two options. We get x is equal to and y is equal to. I definitely, for the y, want to enter in this equation. So y is going to be 10 minus 0.5. Now it says t squared. The t button is the same as the x button. If you're in function mode, you hit the second button in the second row, you get x. If you're in parametric mode, you hit the button in the second button in the second row, you get t. So we want t squared. Okay, so here we have our equation. Y is equal to 10 minus 1/2 t squared. In this particular mode, we have to put something in for x. I'm going to make x is equal to 0, and you'll see what that does. Okay, if I hit graph, I get, it looks like nothing. Nothing happened. Well, in fact, the path is along the y-axis, so there is a little trick we can do to sort of see it. If we arrow over, and instead of having a graphing style of just a straight line, hit enter once, you get a bold line, hit enter again, and you get this, I call it a moving football. And that shows the motion. Now, if you hit graph, okay, and we see the particle moving down the y-axis, okay? To help make this a little bit more visual, go to Window and select the X-min. Notice that T is already sort of selected for you. Select the X-min just to be -1. -1. Okay, the Y or the X max is still 10. The X scale is still 1. The Y min is still -10, and the Y max is still 10. But if you hit graph now, you'll see the ball moving down the y-axis. And that's what this particular function does. It says y is a function of t when t is equal to 0. We know we're at position 10. And you can actually trace along this parametric motion as well. You hit the trace button. At t is equal to 0, we see y is equal to 10. At t is equal to 1, just hit the 1 button. Then y is equal to 9.5. If t is equal to 2, we can sort of figure this out. Let's go back over here and just think what would happen if t is equal to 2. Y of 2 would be 10 minus 1/2, 2 squared, which is 10 minus 2, which is 8. Okay, so if we just hit enter, sure enough, we get y is equal to 8. We see the particle moving down the y-axis. If t is equal to 3, we're at 5.5. If t is equal to 4, we're at 2, and so forth. Okay, so the particle, again, if you just hit the graph button, you'll see the particle moving down. If we can do this again, let's see, go to Window. Okay, we got t is equal to 0. That looks good. I just hit graph. I want to see my moving football again. Change the t max to 6. And then hit graph. There we go. Particle moves down. It seems to be dropping faster and faster and faster, which is typical. If you throw a particle up in the air, it reaches the apex, and then it falls faster and faster and faster, according to gravity. Okay, at any rate, this is an example of a particle moving in rectilinear motion. And let me go ahead and take away a lot of this stuff. We want to analyze what's going on. And the first thing you need to realize is that when you're in rectilinear motion, y is this function of t. The derivative of y is going to be the velocity. So the derivative of position, this is a position function. The derivative of position gives us velocity. So the 10 drops out. The derivative of 10 is 0. And the derivative of minus 1/2 t squared is minus 1 t. So this is our velocity. And if we take the derivative of that, so the derivative with respect to t of the velocity, that sort of looks awkward, is now, the derivative of 0 is still 0, and the derivative of minus 1t is minus 1. This is the acceleration. Okay, acceleration. By the by, this notation, the derivative with respect to t of the derivative with respect to t, is typically called the second derivative. You see the dd, and then dt squared, dt. So that's the acceleration, and you could just write that as a is equal to negative. Okay, so differentiating position gives us velocity, and differentiating velocity gives us acceleration. Good, so far so good. Not a lot of stuff going on there. Let's look at one of the free response problems, and then I'm going to ask you to do some work at your desk there and see how well this plays out. Okay, so go to your handout, and we're going to look at the runner problem first, the 2000 problem. Make this a little bit bigger so we can see it. It says two runners A and B run on a straight racetrack for 10 seconds. The graph above, which consists of two line segments, shows the velocity in meters per second of runner A, and you'll see that off to the side here. So this is velocity of, this is velocity of runner A right here along the side. Okay, velocity of runner A. And what else is going on? The velocity in meters per second for runner B is not shown. It's just given by this formula, V of t, 24t divided by 2t plus 3. Okay? So the first thing they ask is find the velocity of runner A and the velocity of runner B at 2 seconds. So we need, this is 2000, part A. We need the velocity of runner A at 2 seconds, and we need the velocity of runner B at 2 seconds. And that those are the two things that are asked for in part A of this problem. Well, now, the easier of the two is probably runner B. We were told that the velocity of runner B is given by this formula, 24t divided by 2t plus 3. So could you now at your desk find the velocity at 2 seconds of runner B? Go ahead and do that. I'm going to pause this and count to 30. Pausing. Okay, and now we're back. And obviously you should be able to put 2 in there without a lot of difficulty. 24 times 2 is 48, and 2 times 2 plus 3 is 4 plus 3 is 7. So 48 over 7 is the answer. And you just might want to note that on these free response problems, this is also correct. You don't have to do the arithmetic. If you want to leave it that way, you would get full credit. However, we better go back to the problem. It says also indicate units of measure. So all we have now is a number, 48 over 7, but we don't have units of measure yet. So let's think. In our idea of derivative, we need, for velocity, we need the derivative of y with respect to t. And both of these have units. So we're going to have to figure out the units of the distance and the units of the time. Units of distance are going to be on top. distance, and the units of time are going to be on the bottom, and that will be the units for our velocity. So going back to the problem, we found that the velocity is given in meters per second for both A and B. So sure enough, this is going to be meters per second. Make sure you include that, meters per second. Okay, so we've got velocity of runner B taken care of without a lot of difficulty. Okay, velocity of runner A, a little bit more intriguing. Here's the picture. We want to figure out how high this point is when t is equal to 0, t is equal to 2, t is equal to 2, what is the velocity? That's our task. Now, it appears to be some number over here around 6 or 7. In fact, it is neither 6 nor 7. We're going to have to use a little bit of algebra here to figure this out. Let's look at this line. This is a line. If we knew the equation of that line, we could simply plug 2 in for t, and then we'd have the corresponding velocity over here, right? So how would you find the equation of that line? Well, we have a point. It goes through the origin. And we also have another point that gives us the slope, right? The slope of this line, again, I'm thinking algebra 1 here, no calculus. This rises 10 and runs 3. So the slope is 10/3. Okay, because this is going through the origin, the intercept down here is 0. So if you want to think y is mx plus d, like you were in an algebra 1 class, you'd probably say 10/3 x plus 0. But in point of fact, there in this problem, I don't see any y's or x's. So it's probably better to think v is equal to 10/3 t plus 0. So here's the velocity for runner A. It's given graphically, but we can actually calculate it pretty easy by given the fact that we have these 2 points. Okay? So once you have that, and you have that written down, then it's pretty easy to answer this question. So the velocity of runner A, here's the equation again, velocity of runner A is given as 10/3 t. So velocity of runner A at 2, we'll go ahead and calculate it. I'll give you 10 seconds to do that. Okay, so easy enough. We get 20/3. 20/3. And again, the units are meters per second. Meters per second. 20/3. And you can leave it as 20/3. If you wanted to write it as a decimal, you can, but there's nothing wrong with this. Okay, so part A is complete. Part B, find the acceleration. So part B now is the acceleration. We need the acceleration of runner A. Acceleration of runner A. Runner A, and that's also going to be at 2 seconds. And we need the acceleration of runner B. Acceleration of runner B, also at 2 seconds. Okay, so let's go back to the graph. And the idea, remember the idea that we had that the derivative of velocity is the acceleration. Derivative of velocity is acceleration. In this example, this was our velocity, and we could get to the acceleration pretty quickly. For runner A in our problem, we knew that the velocity was 10/3 t, and that was in meters per second. So the derivative of this velocity with respect to time is the derivative of 10/3 t, which is simply 10/3. Now, once again, we need units. The problem was pretty specific. Include units in your answer. So let's see. The units of velocity were meters per second, and the units of time was seconds. So the units here are meters per second, and that would be perfectly acceptable. Okay, so the acceleration of runner A at t is equal to 2 is 10 thirds meters per second per second. The physics people know that meters per second is often meters per second squared. You wouldn't have to do that. Meters per second is perfectly acceptable. Okay, so that takes care of the velocity of runner A, and we got that from knowing the equation for, the acceleration for runner A, and we got that from knowing the equation for the velocity. Okay, how about acceleration of runner B? I'm going to do this two different ways. One way, we have, let's see, the velocity of B was given. Again, we'll just look at the formula. It said 24t divided by 2t plus 3. And we need the derivative of that. So, how would you do that? That looks like a quotient rule problem to me. And then once you have that derivative, you can simply put in the value 2, and you will get the answer. Okay? Now, we're going to do this one by hand, but frankly, it's much easier, much easier to do this on the calculator. So remember, one of the things that the calculator will do, let me just go back to my home screen here, home screen on your calculator. The calculator finds derivatives very quickly. If I were to do math 8, that says numerical derivative. Now let me pause this here just for a second because I want to bring up another document. Okay, I'm back. I found a copy of the instructions for the free response questions. You'll get a full copy of this as we get closer and closer to the exam. But I wanted to point out a couple of things. Note that you are permitted to use your calculator to solve an equation, find the derivative of a function at a point. Remember, we're asked to find the derivative of velocity at t is equal to 2. So we're supposed to do that. Or also calculate the value of the definite integral. Those are the three things you're allowed to do on your calculator. However, if you're going to do those things, one of the things the College Board graders insist upon is you must clearly indicate what they call the setup of your question. What's the equation you're solving, or the function that you're trying to find the derivative of. Okay, so we're going to do this on the calculator. And so we have our calculator here, and we'll just back this up a little bit. We're trying to find the derivative of velocity at t is equal to 2. So what we should do is we should write down the velocity equation, which we have. We don't care about this now. We're not going to use the quotient rule. Instead, we're going to go directly and say the derivative of velocity at t is equal to 2 is a number. And we can do that on the calculator. So we want the numerical derivative of 24. Now, if you want to put t in here, you can. If we did that, we'd have to do alpha t, 24t, divided by, and then make sure you have parentheses here, 2 alpha t plus 3, like that. There's nothing magic about using t. However, if you do that, the next line in your numerical derivative should be the derivative, or it should be the variable alpha t. And then lastly, the particular point, t is equal to 2. Right? So that would be our numerical derivative, and the calculator gives us the answer. It's 1.4693877875. Looks rather awkward. As long as we get it to the nearest thousandth, we'll be okay. 1.469. So that's a good approximation. Make sure you include the units, and we noted that over here, right? Just like for the acceleration of runner A, this is going to be meters per second squared. Let's suppose we didn't know how to do that, and we were stuck by doing it by hand. At that stage, we would have to, in fact, get the derivative using the quotient rule. Now, there are plenty of problems where you have to do the derivative by hand. So let's quickly review the quotient rule. The derivative of a quotient is the bottom, 2t plus 3 times the derivative of the top, which is just 24, minus the top, which is 24t, times the derivative of the bottom, which is just going to be 2. And all of that is over the bottom, 2t plus 3 squared, right? Bottom derivative of the top minus top times the derivative of the bottom, all over the bottom squared. So this, in fact, is our acceleration function. Now, again, let's suppose we did not have our calculator, and we just need to figure out what is the acceleration at 2. Well, the answer is you simply plug 2 into here. So dv dt, evaluated at t is equal to 2, works out to be, we're putting 2 there, we're putting 2 there, and we're putting 2 there. Okay, now you don't have to do the arithmetic, but I'm going to do a little bit. 2 times 2 is 4, plus 3 is 7 times 24. And over here we have 2 times 24, which is 48 times 2. And on the bottom we have, again, 7 squared, which is 49. So there's my answer. As long as I have the units, I would get full credit, meters per second squared. Okay? Now, just to sort of show you that we're not, making things up here, if I were to look at 7 times 24 and take away, 48 times 2 is 96, I can do that in my head. And let's see, I need another set of parentheses in here. Okay, so 7 times 24, take away 96, divided by 49. Lo and behold, I get that exact same approximation. Now notice this is probably a little bit more accurate. The second one, the first one was fine to the nearest thousandth. In fact, it was probably fine to the nearest 10,000th or 100,000th or millionth, and it was off by 1/10 millionth. But the approximation is good. You could leave it like this and get full credit, no problem. Okay, so there's part A and part B. Not a lot going on. Part C is now the interesting part. So part C asks to find the total distance run by runner A and the total distance run by runner B over those 10 seconds, indicate units of measure. By the way, I would hope that if you're thinking distance and units of measure, that should be pretty clear. That's meters, right? The units of measure will be meters. That's the distance run. And we just have to come up with the number. Okay, so let me pull up a blank screen here and sort of do a little bit of theory before we work these out. And I think this is a rather important concept, so I'm going to hang on here just a little bit. Remember the fundamental theorem of calculus. We've looked at this a number of times. If you integrate from A to B some function that's a derivative, you get f of b minus f of a. Integrating a rate of change gives net change. Now, for our problem, we are integrating a velocity. So let's suppose our velocity now is dx dt. So we're supposing that our position function is along a horizontal x-axis. This is our velocity. We're integrating with respect to t. And if we go from 0 to 10, we're going to get x of 10 minus x of 0. So it's exactly the same as this, right? Instead of a and b, I'm using 0 and 10. And instead of the prime notation for f, I'm using the differential notation dx dt, like that, okay? I suppose if I wanted to, I could have done x prime like this, x prime of t dt, and that might match up a little bit more closely with what I have here. Dx is dt, f prime is x prime, and the independent variable is t. At any rate, the idea here is if you integrate velocity, you're going to get net change in position. Now, assuming that the initial position is 0, we're starting at 0, this simply gives us how far we've run. Okay, now how do you do this integrate? How do you do this integrate the velocity? Well, for runner A, it's simply an area problem. All we have to do is calculate the area under this velocity curve, and we can do that by just counting boxes, if you will. I would probably suggest if you break it up into a rectangle and find the area of this rectangle, and then find the area of this triangle, that may be the easiest way of doing it. Some people may like trapezoids, but let's do rectangles. This is 7 seconds going this way, right? 3 to 10 is 7 seconds. Let me go ahead and write in seconds. And the velocity is constant. It's right up here at 10 meters per second. So this height is represented by 10 meters per second. And if you multiply, you know how to do areas of rectangles, you multiply length times width. So 7 seconds times 10 meters per second. Well, lo and behold, the seconds cancel, and you get 70 meters. So this particular rectangle gives us 70 meters, and we have it done. Now for the triangle, a very similar multiplication problem. This is 3 seconds times the height, which is 10 meters per second. So 3 times 10 is 30, but we have half that because it's a triangle. So this represents 15 meters. The total distance run by runner A is simply 85 meters. So I suppose we should write that down somewhere. Part B, part C. Oops. Come on, buddy. Okay, part C. So for part C, distance run by A, t is equal to 0 to t is equal to 10, is going to be the integral of the velocity of runner A, right, from t running from 0 to t running to 10 seconds. And the way we did that, we did 15 plus 70, right, which is 85. I suppose it wouldn't be terribly bad to say this is 7 times 10, and this was 1/2 times 3 times 10, just to sort of show where those numbers came from. Okay, so that's the distance run by A. How about the distance run by B? A little bit more intriguing. Distance run by B, again, same t is equal to 0 to t is equal to 10 seconds. We're going to integrate the velocity. So we're integrating from 0 to 10 the velocity dt. Okay. Now here, this is a much more difficult integration problem. 0 to 10 of, what do we had, 24t divided by 2t plus 3. That was the velocity. Now, I don't know that there's an easy way to get that antiderivative. Okay, there's probably some integration techniques that can get you there, but remember, we don't have to find the antiderivative to do that. One of the things we're allowed to do, right? Here's our directions again. We are allowed to calculate the value of a definite integral, so we can do that as long as we show the integral. So we have to show the integral that we're using. And we've done that. We've got the integral using right here. Okay, so all we have to do is just dump that into our calculator. And I don't know of any other way to do this, frankly. That would be easy. So math 9. And again, our function is 24. I'm going to use t, again, 24t divided by parentheses 2t plus 3. Okay. Now, just as an aside, if I hit my mode button, I notice I'm still in parametric mode, and that t sort of popped up on its own. If I were in function mode, which I could have been, oops, function mode. And then if I try doing this again, math 9, if I'm going to hit the second button in the second row, I'll get an X. That's okay. It really doesn't matter what this variable is. It's called a dummy variable. So we're dividing this by 2x plus 3. Okay, comma, we need to specify the variable, and then we have to specify the lower and then the upper limits, so 0 to 10. So you have to write it in mathematical notation. You have to write this on your sheet, and then after you write that, you just use your calculator to get the number. So you just hit enter, and there we are, 83.336. So 83.336 meters. Okay? Now, one of the things I would like you to do, we've got about 3 or 4 minutes left here, tonight, go onto your class page and find this problem from 2000 and look at the solutions. We've got the solution all here. Look how the points are allocated. I think it's important to understand what the graders are looking for. They're looking for not only the correct answer, but your work on getting there. So part A, you know, this type of work would be reasonable. Part B, this type of work would be reasonable. And you're going to be writing a lot of stuff. If you just write answers down, don't expect full credit. Okay, I'm going to stop this little video here. Again, I'm going to try to put these recorded lessons together over the next week or so. So when I'm out, you'll have at least my voice, if not my presence, to work through some of the topics that you need prior to the AP test. Okay. For the AB folks, I'm still here. For the BC folks, I'll see you tomorrow on Friday. Bye-bye.